Okay, good morning, good afternoon, everyone. Thank you for this opportunity to talk to regarding CHPC and data centers and maybe sustainability. My background is a little bit varied. I came from the Intel manufacturing facility in Rio Rancho, and then moved to PV and started doing some R&D on some new PV technologies. Joined the Renewable Energy Industry Association in New Mexico, and then had a wonderful opportunity to actually be involved in the Facebook/Meta data center in Los Lunas, New Mexico, which I'll talk a little bit about today. In 2017, I came here to the CSIR to head up the PV team and start a PV module quality and reliability test lab, which is just around the corner. So we're trying to support the PV industry in South Africa and Southern Africa with ISO 17025 world-class testing results that would otherwise have to go overseas. So we're trying to localize some of that technology here. So with that, I'll go ahead and get started. Got a lot of stuff to hold on to here. So the CSIR is where we are now at the ICC. It's a national science council. Many of you know more about it than I do. I'm a relatively newcomer, but we do research in a lot of areas. We're organized in 9 clusters. One of those clusters being the smart places where I sit. Within the smart places, there is the Energy Center, which is a fairly new center, maybe 5-7 years old, let's say 7 years old, with a focus on energy and really, I mean, honestly, it's renewable energy is the focus. We don't do a whole lot in traditional energy supply. On the energy supply and demand team, where I fall, we focus on this kind of work, and there's a link to our PV module Q&R lab. You can just go to YouTube and search on CSIR PV module testing, and you'll see the link there. Press and wait. There we go. Did it move? Okay. You warned me. I listened, but then I got impatient anyway. Sorry. This over here this is a map of the CSIR. That's the CSIR campus map, and I've just overlaid some colors on there. It's a fairly big, it's a 2 kilometer by 1 kilometer space, and all the colored labels there are places where we've had an impact as the energy center on campus. So you can see, for example, we have a single axis tracker there and a dual axis tracker there. You see those when you drive by the N4. You'll see those trackers. In the orange here, we've got a megawatt of rooftop PV, and then we've got the plans to do these additional buildings. This is where the energy center sits. This is the ICC here, where we had one of my colleagues had designed an innovative system to reduce the electricity bill for cooling. So it was a water storage / ice storage way to sort of pre-cool the air before we run it through the electrical AC. Down here is the PV lab, and there's another 30 kilowatts of PV on a dual axis tracker there. So we've also got electric vehicles running around campus. So we've had a pretty good impact on the sustainability, or at least on the reduced electricity consumption here at the CSIR. Here's the history of our PV plant. PV production on campus started with the single axis tracker that's on the N4 and the dual axis tracker and the building 17 rooftop system. And then our last system in 2019 was this, for what we call phase 1. It was almost a megawatt of PV. So now we have about a total of 2 megawatts of PV that are powering the CSIR. And so you can sort of imagine, we've had some discussions now with Ricardo. Just yesterday, we're trying to come to an agreement to assist with some design sort of feasibility business case studies for PV to support your data centers in Rosebank and throughout. So that's why I'm here. I mean, that's my link. I'm not just some random guy who's talking about PV. Okay, so hopefully we can take some of what we've learned here on how we design and how we procure and manage PV systems to help you do the same at your data centers if that becomes a desire.
So we're thinking of doing that in the UK, actually in Cambridge. So
I'm happy to come to the UK as well. Huh? Yeah. All right.
We're building a big PV, like 30 megawatt PV.
Good. Okay.
And I think there's talks with linked into my data centers. Let's talk.
Yeah, sounds great. And so what you can see the upside on this here. We've got the blue line here is the capex that we spent. So we started at 11 million and we're up to about 34 million in investment as the CSIR. And that's brought us the red here, which is about 17 million in savings so far. So our electricity bills have reduced by 17.5 million since we started this program. And then this is the cumulative energy generation. And these, you can see where these charts are going. The red and the green line are going up here, right? And the blue line is not growing anymore. So at some point, we'll break even and cash flow positive, right? So that's an exciting time for us as an energy center, because that's kind of money in our pockets to do other stuff, other cool stuff. Yeah. And so we produce only about 12 to 15% of our total consumption at this, 2 by 1 kilometer campus is from PV. It's a start. It's a pretty good start, but it's nowhere near, most of the energy. This is what we see this is what a typical load profile or daily profile looks like. This is a week before COVID, and this is a week after COVID, I should say, the national lockdown on April 1, 2020. And what you see here is the basic, the energy consumption that we saw under normal operations versus what we saw under lockdown, right? I mean, the base load dropped, the peak loads completely vanished, but the PV kept generating, right? Which is cool. They didn't care. The photons don't care during the lockdown. So what you see now is over here, you see, a big chunk of blue, which is the power that we buy from Swanee, and a little bit of this multicolored, rainbow thing here, which is the different PV generators. And then when your base load drops and your peak loads disappear, now you start to see our PV eating into the power that we purchase from Swanee every day, right? So it's kind of a cool thing there. One of the things that we learned, yeah.
So is most of that? Is this nighttime?
Yes, nighttime. Yeah, exactly. So the black line is irradiance. So that's where we're measuring sunlight there. That's our fuel gauge. How much fuel are we putting into the generators? That's the black line. So this is what kind of a sunny day looks like. The sunrise, solar noon, sunset, nighttime. Exactly. What else do I want to say here? Oh, so one of the things we learned here for us too is, our savings calculus includes reduction in kilowatt hours purchased and shaving that peak demand, right? So when you ask for 5 megawatts of PV from ESCOM, they charge you a premium, right? So in March of 2020, we saved 115,000 by reducing our peak demand from the PV. But in April, our peak demand went away. So that savings was 155 Rand. I mean, that's barely a dinner. So it's just an important thing to think about as we go into the planning phase on this. What are you really going to get back? What are you really going to save? And it depends a lot on, and also interestingly, during COVID, the city of Swanee implemented some changes to the tariff structure such that we don't really gain anything by peak shaving anymore. So we basically pay for 7 megawatts like all the time. So the only way we get the peak savings anymore is if our load exceeds 7 megawatts, which you can see here, it doesn't even reach 5. So those are really important things to think about when you're doing the business case. Now here we're just going to look at some trends. This is kind of what you might expect from an energy generation on a single plant, right? So if you decide to put something on your rooftop in Rosebank or elsewhere, this is the kind of stuff that you're going to see. The seasonal variability in the output changes, right? So you're going to get more energy from that system in the summertime than in the wintertime because the days are shorter in the wintertime and the sun is lower in the sky. So that's going to happen. And then that's about all I really want to say on here, other than, there's a few issues. There's a challenge in O&M, and that's really, this is a slide deck that I've been recycling a lot lately. PV is not plug and play. You can't just put this on the roof and forget about it. Things happen. And if you drive by the N4 and you look at our dual axis tracker right now, you'll see what I'm talking about. We got a lot of trackers that are like not too sure where they want to be. So that's a maintenance issue, right? We got to deal with that.
So what, the blue and the black?
So the black is the left axis here. It's the kilowatt hours per month. And so in this would be kind of our summertime, December, January, February. This is our wintertime, back to summer, back to winter, back to summer, back to winter. So that's just because of the amount of available sunlight. And then the blue line is the performance ratio. And so this is just a means to track sort of normal performance. So it's really a statistical process control chart, if you want to think about it that way. So, I spent 6 years at Intel in a manufacturing facility, and every single thing that they measure is on a control chart. So I'm obsessed with them. But they're really valuable. I mean, if it's good enough for Intel, it's good enough for me, right? I mean, there's billions of dollars coming out of that factory every day, and it depends on keeping everything in control. So it's a way to simplify all the variability that you would otherwise see in a PV system and get something that resembles a reasonably flat line. So when you're monitoring this thing, and if you're doing it on a daily basis and you see, oh, yesterday, that blue line dropped off the charts, something's wrong with the system, right? So it's a way to indicate the health of the system. So performance ratio is a pretty standard, is a standard metric in PV, but the basic idea is to create a metric that should be stable under normal operations so you can identify out of control signals, which I'm sure you guys at the data center have a lot of metrics like that, right? By the way, I'm also a very happy and satisfied user of your CHPC. I don't know where I'm going to, but when I log into Lanao, I guess I'm going to Rosebank. So I'm using that. I'm doing a PhD on machine learning. So how to basically take in electroluminescence images, which are like X-rays for PV modules. So we can see all the bumps and cracks and defects in a PV module with an EL image, which you can't see with your eye. Just like when a doctor takes, do you have a fracture on your arm? He takes an X-ray, she takes an X-ray and says, yeah, you have a fracture. There's millions of these things being produced every single day across the planet. There's not really any good software to analyze them. So that's what my PhD is, and I'm using CHPC for that. So thank you very much for all that great work. This is the dual axis tracker. And so to your point, this is where the blue line becomes interesting. Same idea, black is energy production. On dual axis trackers, we don't quite get the seasonality that you see on the single axis or fixed tilt because the modules are always looking at the sun. So the performance ratio, the energy output stays pretty flat. And what you notice here is that the blue line is quite good. It's also a bit higher than the previous system. And then bam, we got problems. Oh, we got more problems. We recovered a little bit. We got problems. We're trying to figure out how to repair our trackers. We got some motor issues. So basically when our motors started to fail, our performance ratio went down. So the performance ratio is basically, energy produced relative to the size of the plant, relative to the available sunlight. So when that metric,
data or clients that went down there?
Sorry, I missed it.
Missing data.
Missing data. So this is a chronic problem for us as well, is to maintain, we've got multiple systems scattered throughout the CSIR built by multiple contractors, and they all put in their own systems. And so if, we might find that either the weather station went down or the AC meter went down or something with the inverter system went down. It can be as simple as nobody topped up the data contract, And so when you lose that data, it's gone. And so we do struggle with that. And I'm basically trying to show you here that we can explain all of the outliers. So we understand the system. And then when things happen, we'll at least know something happened. We have a history of what's happened in the past. We can look to see if there's any common signatures and move forward. Basically learn from it, right? So the out of control points for an Intel engineer was a pain in the neck because it meant you were not going to go to your Friday night ride or whatever, but it was a great opportunity to learn because something just happened on a process that you're not aware of. And so, we try to take that same approach. Did that answer your question?
You did, but I was just wondering why, if missing data, why do you present that as outlier?
Well, I could have removed it from the chart, right? I guess I could have just removed it from the chart, but I think I keep it here because it's a known problem for us, and as long as we're tracking it, we will have some.
In the back of your mind.
I'll forget about it if I take it off the chart, right? So it's just like, yeah, I think that's really where it's coming from. And then this is the rooftop PV system. You'll see scattered around. We've got six rooftops now that have PV on them. This is the latest one. It's all grouped into one. So there's actually 5 buildings here represented. Same story. Issues here. Well, one important issue here was this one. So 50% wet leakage failure on the PV modules. So this is something to think about if you're going to scale up and go big on PV. Make sure you're buying good quality components. It's not just the modules, it's the inverters as well. Our PV test lab is here to help people who are putting a lot of money into PV to make sure they're getting the right modules. So we took a small batch that, I don't know, there's 3,000 modules or something like that on that last system. We measured 10 from the first batch, and 50% of them failed the wet leakage test. This is a really important safety test. It's like it's not a certified module if it fails the wet leakage test.
Sorry, have these gone past SABS?
SABS, I mean, when they are brought into the country and yet there's this, or what is that? Is it SANAS or all those institutions?
Yeah, good question. So SABS is not involved in PV module certification. We've had a lot of discussions with them early on, and they insisted that they weren't going to invest hardware, and they were deciding whether or not they were going to build a program. But if they did build a program, they were going to use the CSIR as the testing facility, so it wouldn't duplicate. But they didn't build a program around it, so it relies on, and I would say, like, honestly, most of the world, the modules have certification from the IEC. So the IEC, there's a set of international standards. You guys probably have similar, if not IEC standards. I don't know, we maintain 20 or 30 IEC standards for the work we do in PV. And these are the standards that are used to certify modules for sale globally, and so that's where it comes from. So you want to make sure that you have an IEC certified module for sure at a minimum. But all that means is that some small tiny fraction of the modules that were built with the same bill of materials went through certification. Doesn't mean the modules that you're going to buy went through certification. Almost certainly it doesn't, right? So what we're trying to raise awareness of here in South Africa is that quality varies from batch to batch, job to job, factory to factory, shift to shift. And it's true, and not just in PV modules, right? So even though you have a module that's been certified, you may not be buying the same exact module, because since the certification and now, the module manufacturer has found a cheaper supplier for the EVA, or they've changed their soldering process, or shaved 30 seconds off their lamination step, thinking it's okay. So what we suggest to the clients that are putting a lot of money in this is that's why you got to do batch testing. And so so if you're gonna put 10 megawatts of PV up, get an independent test lab to pull a random sample of those things and do some of these basic tests and make sure that the quality of those modules is consistent with a certified module. So that's the approach, and that's the approach that globally people are taking. There's a few, so this kind of reliability testing or pre-construction reliability testing is a big deal when people are building big PV plants.
It's a scary thought, though.
It is a bit scary, especially for the homeowner who's, it doesn't make financial sense to spend 50,000 rands on some testing when your PV system costs 75,000 rands. But when your PV system costs 10 million rands, it makes sense to spend 500,000 on some quality testing. And IRENA put out a report and they looked at a bunch of different PV plants with and without pre-construction testing in the contracts. And they found about a 3% increase in output on the PV plants that had pre-construction testing in the contractual agreements. Because what happens now is the manufacturers are like, okay, you're paying attention, you're going to get my A-class modules, but this guy over here is not asking me for any independent testing, so I'm going to send him my B-class modules. They all work, some work better than others. So the testing isn't the magic part. The magic part is let your suppliers know they're going to be held accountable. Just like putting a ref on the field during FIFA. Imagine if the refs weren't there. Oh my goodness.
Lawrence, do you?
Do you have some methodological testing currently underway within the Energy Center that might be commercialized at some point for PV testing?
So
in negotiation or in collaboration with the SABS?
So we prefer to stand on the shoulder of the giants who've written the IEC standards. So we just take a subset of those. So a certification test for a PV module, batch of PV modules costs about $50,000 to $70,000 US. This was my business before coming here. Yeah, So what we do is we take a subset of the tests where we know that failures are most likely to occur, and we do those. So we're working with some clients right now that are building 3 power plants, and we're doing a batch testing for each of the 3, and each of one of those is valued at about 250,000. So that 250,000, the way I think about it is, there's an O&M budget associated with the PV plant, as you can see all the problems that we have, right? So if you roughly estimate what you expect to pay and what you're willing to pay for O&M on any given year, then that should be about what you'd be willing to spend on your upfront testing. Because if you can do that upfront testing and rule things out like this leakage failure, you're going to save that money over the next 25 years.
But you do have some sort of mitigation whenever you purchase or procure those PV channel.
So that's going to depend on the procurement. And so that's why the contract is really critical, right? I mean, so the one thing that you hear people talk about all the time is the 25-year warranty. And then if anybody's ever dealt with a 25-year warranty on a PV module, they're like, it's almost not even worth your time. Because half the time those PV module manufacturers aren't around. So we're trying to say, and then if you do file, there's I think I'm hearing there's rules like you got to go to the country where the panel was made to file your claim. So now we're going to, I mean, let's face it, we're sending people to China now, right? So we've got an office in China that's just doing warranty claims. So it's best to avoid it. It's best to avoid it. And I think a lot of people kind of see that. And there's some, we can't catch everything, but this one was so easy. And we went back to, we just cut the junction box off. It was leaking through the junction box. We cut it off. We looked at there's a silicone seal that goes around the junction box. It glued onto the back sheet. Somebody somewhere decided that a vented junction box was a good idea. So this is an electrical piece of plastic that's meant to isolate, that's meant to prevent electrical current from flowing between the inside and the outside of the module. They vented it. So now there's a path to the outside world. They forgot to seal the center part. Bam, it's just pouring water inside of it. So simple mistake from an otherwise, it could have easily been, I can't say who it was, but it could have been a tier 1 manufacturer. They made a change to their process, didn't think it all the way through. And okay. The other, this one was kind of funny. The installer, well, this was actually our fault. So we have a bunch of distributed AC units on the rooftop, these split level units, which are brilliant, by the way. In order to prepare for this one building, we had to move those, so we could put the PV down on the roof. And I think somebody installed 10 of them on one of these parapet walls, and the parapet wall went. Just couldn't hold it up.
So on the, I know, on the lithium ion batteries, I'm sure if you have this problem on the panels, how much more problem you have on the quality of the battery itself.
Yeah, I think that's another issue, and actually there is some work going on right now with the Energy Center in conjunction with the Belgian government. Vito is a research, anyway, we're building a battery test lab here to do similar kind of work. Yeah. Okay, so I'm going to move on now to data centers, and which is I think all of your interests and how these things come together. And I just have to go back to Los Lunas, New Mexico, where I'm from. So this is just 60 miles from where I used to live. This is my son's car, so proud daddy moment. He built this plant. He was, part of the team that built this plant. So his company builds megawatts of PV. One small company in New Mexico is building tens of megawatts of PV every year. So it's really kind of incredible. Now, there was also, I think you mentioned earlier, this joint partnership and how this stuff can work. And that's really a fascinating part of this, right? So Facebook, or is it Meta, comes in with pocket full of cash, just a truckload full of cash. And they want to build a data center, but that data center has to be powered by renewables to meet their obligations to stockholders and consumers and whatever. So they identify, the Southwest United States as having good solar resource, also very good in terms of evaporative cooling. So this plant actually has some really creative cooling mechanisms using like a series connected evaporative cooler, which is low on energy, high on water use, but it allowed them to reduce their electric bill, right? So they're working sort of secretly with 5 different states and the utilities in those states to come up with a deal to basically broker a deal, right? So our utility, which is PNM, which is your ESCOM, basically had to agree terms of this thing, right? So it was like 5 states all trying to put these public-private partnerships together to enable Facebook to build the data center with the energy supply that they wanted. So it was a cool project. New Mexico won it. And this is what it looks like on Google Earth Pro today. This is the first, my son calls this Facebook 1, right? So that was Facebook 1. The plan was to build 10 megawatts now with the plant, do another 10 megawatts in 6 months, 10 megawatts in another 6 months, and all in conjunction with the utility, right? So the utility is like, okay, we've got land and transmission capacity over here, so put your plant over there. And then through accounting, every kilowatt hour that those PVs generate, in total covers the total annual energy consumption of the data center. So that's how they did it. And every time they expand the data center, they put up more PV. So they come with the money, PNM comes with the grid, and the state signs off on it, right? Because it's a publicly regulated
So
utility.
what do they do at night?
So at night they buy from the grid.
So they buy from the grid.
Yeah. So they've got enough PV to produce enough 24-hour energy.
Excess.
Yeah, so they're sell to the grid at night and they buy back during the day. But did I say that the wrong way? I think it's the other way around.
So they've got excess generation capacity during the day that they sell.
Yeah. Yeah.
Okay.
And the cool thing is they're all over the state, so they're not just co-located. So they've got that agreement. So it's obviously a massive complex agreement. A lot of people had to sign off on it, but that's how they're doing it. And I think, for me, one of the things about South Africa is, they could do this because we have the same solar resource here as we have in New Mexico. Sorry, England, not so much, right? So it sucks.
In the winter, what? In the winter,
The sun doesn't set in
it's-
England.
it gets light at 8 o'clock in the morning, it's dark by 4, and the
Yeah.
sun's pretty shit in between. So yeah, I don't know how you do that in the UK. I guess you have to have
You just have to have more
a
PV. That's
lot
it.
of excess PV.
More PV and wind. I mean, wind is, we get to work on some wind projects as well. When you mix wind and solar on a mini grid with battery storage, it's amazing what the contribution wind can make because that can blow anytime. So it really takes a strain off the battery system. So that's the idea here. And I just, I couldn't believe it. I was like, seriously, a kilometer? I was like, Aiden, is that thing really a kilometer long? He's like, yeah, it is. That's one of them. So I don't know, they're up to 10 now. They've got 10 of these plants scattered around the state now and they're doing wind.
So it's 1 kilometer by.
This was about 300 meters, 300 meters,
What's the generation capacity of that?
10 megawatts. So that's a 10 megawatt
What
plant,
does
yeah.
that cost in dollars?
What are we at now? Like,
A megawatt is.
I can only think rands now, right? So it's, I forgot what
Tell me
dollars are.
rands, I'll work it out. So what's-
Yeah,
what's that
15, I
cost?
don't know, 15 rands a watt. So 15 million rands for a megawatt.
15 million.
150 million
What's
rands.
that in pounds?
It's about $1 million.
The capital
A
cost.
buck a watt, that would be 10 cents a watt. That's pretty
I'm
cheap.
talking about the capital cost to deploy that.
Yeah. No, so if you go up to, so NREL, which is a research lab in the States, they benchmark all this stuff, right? And so that's a reference for us right now, and it's in that order of,
15,000.
per watt, rands. So this is my colleague Manjanath, so also a
To
contributor.
buy the capital cost.
Yeah.
Of the PV.
Yeah.
That's
The whole system, the whole
the
system,
system.
the whole system.
That was what, 15 million rands, so yeah.
A megawatt is not compared to what you pay
15 million.
for power
It's about
from
£1 million
Eskom
a megawatt.
coming in.
Yeah.
Less than £1 million. And how long was the service life of that?
So that plant should be running for 25 years. That's usually what a business case looks like. And the PV modules and the racking system, looks like a single axis tracker, which is like one of the ones you had
That's
down
for me
there.
in the UK to buy from the grid a megawatt of power today, with this madness, it's costing me £2 million a megawatt to buy it
Yeah,
in a year.
Yeah.
And that's you telling me that's just £1 million to own it for 15 years.
yeah.
Megawatt.
£2 million a megawatt. Last year it was costing me £1 million a megawatt.
Yeah.
Today it's costing me £2 million a megawatt. By the middle of next year, my electricity generator is telling me it's going to be costing me
Why do
£3
you
million
build a
a
data center?
megawatt.
Haven't built it yet?
Yeah.
Well,
But and there's a reason why solar PV generators, solar PV plants are the biggest component of new build across the
It's
globe.
costing me 30 pence, so that's 45 cents a kilowatt hour. That's what it cost me. That is crazy.
Yeah. And our estimates for our system here is we range between, the 70 to 80 rand cents a kilowatt hour. is what we're producing PV from on these systems.
Lawrence, what's not indicated to us is that some of the panels actually they pave beneath it some white colored bricks, which means there's a reflection coming from below, which means you can still improve the capacity or of that, the output of that capacity as it is on that megawatt, depending on the type of panel you use.
Yeah.
So it will reflect back onto the bottom of the PV panel, and you get an extra bit of more efficiency out of it.
Yeah, so you're referring to the bifacial module, and that's
Okay.
a new, relatively new development, probably only a few years old. It's really taken over the market. So PV technology has changed a lot in the last, certainly on my watch, and even more dramatically pre my watch. But now we're doing 140. We're doing like these 2 meter plus modules, bifacials, half cut solar cells with PERC, and so that seems to be the latest and greatest right now. Every little change gives a little bit of a bump. Bifacials came out with a huge splash, you know, oh my God, you're gonna get 10-20% more energy. Not really, but it's not a zero-sum game. You get something from it.
Excuse me, this question sounds idiotic, but I have to ask it anyway. What are the running costs of these panels?
The operations and maintenance
Yeah,
costs?
operation.
No, that's a really good question. And that's actually one that's very important to me because, you know, I think, you know, PV got a little bit of overselling in the beginning. And that's why every place I talk now, it's like, these are not plug and play. They require operations and maintenance. So I think the euro benchmarking is around $17 a kilowatt per year. So we budget about 300 rands per kilowatt per year. So it's not a lot of money, but it needs to go into the equation. And the other thing that needs to go into the equation are replacement costs. So when we do a business case, we say, okay, what do we expect to pay for CapEx? What do we expect to pay for OpEx? And what's our replacement cost? And we just, as a rule of thumb, we use 15% of the CapEx at around year 10. And then we put that into the models and come up with, and still get very competitive LCOEs. But if you don't get your O&M right, you can blow the whole business case. And so that's been a pretty big learning point for us because, you know, we put this procurement process in place that says we want the EPC to do the first 3 years of O&M in one contract. And what that does is incentivizes, or we believe it incentivizes the EPC to build a good quality system because they have to run it and they have to perform. And if they don't meet their guaranteed performance ratios after 3 years, they're going to pay a penalty. 2 of our 3 did not meet their performance guarantees, right? So that's an important thing to think about when you go into this procurement for your data centers. So after those 3 years, the O&M contracts run out. So we go back to the market and we're like, okay, you know, let's do some, you know, let's put a tender out for some O&M. And it was shocking. I mean, the prices that came back for the O&M were 3 and 4 times higher than what the original EPC contractor said they would do it for. So it's pretty clear to me now that they were using that as a tool to get a lower price on the bid. And they weren't, you know, they were spending more than 300 rands a kilowatt. So
That's 2 square kilometers then, the size of that PV land space.
it's just massive. It's
That's
massive.
the other thing, of course. I mean, in many countries, I mean, in Mexico, I guess the land's worth shit.
Yeah.
But it involves to take up 2 square kilometers in Cambridge real estate.
Yeah, all right. Or in Rosebank. So what I did here was, is I said, okay, well, this is just this rectangle here now is just a megawatt, right? So how much surface area does 1 megawatt of PV panels, you know, cover? And if you overlay that, I've got the right real estate. Huh?
Yes.
That's pretty much everything. And that's, you know, there's no spacing for anything other than the module. So this is a totally, you know, fictitious thing just to impress upon you that a megawatt's not going to cut it. It doesn't fit. And furthermore, it doesn't even come close to covering your load. So just, you know, so that's the module area there for a 1.2 megawatt DC plant. Any rooftop system that you want to put here is going to be a tiny fraction of your load. And we talked yesterday about a 1 megawatt base load. Forget about peak loads, but just assume you got a 1 megawatt base load, which I think is about right for Rosebank. You need 8,760 megawatt hours. That's just the number of hours in a year. And to produce that amount, you know, you're going to need a 5 megawatt PV system. Half of what you saw on that.
That's because of the day-night winter summer.
You gotta be able to produce everything in those limited hours. Limited daylight hours. So for you guys going forward, battery storage is gonna be key, and that's another thing. We work with SAPS and NDOH and UNISA and particularly the Department of Health right now. Is they just want load shedding protection, right? Which maybe is a large part of what you're looking for, and I think that putting all your money in batteries makes the most sense, because especially in this case.
So you're charging your batteries from your solar and using that to protect your own.
Or from the grid.
Or from the grid as well.
Just don't, because you're like a PV system might cost you, let's say a PV system costs you $10 a watt.
Yeah, it's cheap.
PV plus batteries is gonna be another $5, it's gonna be $15 a watt. So take that 10 you would have spent on PV and put it all into your battery bank. And with SAPS, they're worried about theft. So they're like, well, if we put PV on our rooftops, they're gonna steal. I'm like, from the police station? They're like, yeah. So forget about the PV, just open up one of these cells, fill it up full of batteries and lock the door. And then charge that thing at night when ESCOM power is cheap. And then, so that would be a strategy that I would encourage you guys to consider.
So, sorry, the square meter area.
That's an acre is about 4, right? 4,000, right? So an acre, that's just above an acre, right?
It's about right. An acre or megawatt is about right. Yes. Yeah. For the whole plant, right? And really, if you look back on this plant, a single axis track plant is 50% modules and 50% open land. So if you wanted to do a megawatt on this kind of a single axis tracker, you need twice as much land as what I showed before. This number here that I'm showing is just the module size. So it's basically it's 2 square meters per module times however many modules you have. That's all I'm showing in this rectangle here.
Yeah, I think in Cambridge, we're going to be putting that thing out of town.
Yeah.
In some fields that they use for grazing stock.
Yeah.
So they'll still be grazing.
Yeah.
And then they will run a cable back
Yeah.
to the city.
And that's another thing to consider. And I think Ricardo was saying too. It's like I don't see a lot of future planning here, but maybe it's with an eye towards new data centers and where do you locate them?
Yeah.
Locate them where you have some space, or pick up some extra land with you so you can do that. In the best case scenario, you do something like what Facebook did, and you have an agreement with ESCOM that says, we're going to just meter we're going to put this thing, 10, 20 kilometers outside of Cape Town, somewhere out by the airport. And we're going to meter that thing, and every kilowatt hour that produces somehow gets credited to your data center bill. That's the ideal world. And then I think you have a case, because I think one of the things I remember back in this discussion was that data centers make really good customers for utilities. Baseload. Yeah. Doesn't matter if it's 6 in the morning or midnight, it's baseload, and they want baseload. So you have a stick, at least, or not a stick, a carrot, to say, look, help us do this. We've got this baseload. We're going to, help you stabilize the grid. So that's just I think another thing I picked up along the way.
That's what the university are very keen on partnering with us, because we have a nice predictable baseload.
Yeah. Yeah.
And if we run it properly, the phase balancing should be good. There's an issue with phase balancing in HPC data center.
Okay.
In theory, we should be able to balance the phases.
Okay. Good. So I think that's pretty much all some numbers. So I put this is SAM. So I use the system advisory model. If anybody's interested, it's a free download, very sophisticated program, bit of a learning curve, but once you get there, you get all kinds of cool stuff out. So this is that 1 megawatt plant at a 35 degree. System advisor model, or SAM. And if you link that with NREL, National Renewable Energy Lab, they maintain it, and they're always doing updates. It's really a great program. So we use it a lot for financial modeling. Other models are out there in the commercial sector. My colleague Manjunath is an expert at PV-SYST, which is more used in the commercial world. I tend to focus on the SAM stuff because you can do a lot of simulations, right? It's a really fun thing. So you can take code that you sort of create interactively through SAM and download the equivalent Python scripts and simulate to your heart's content. So it's really fun. So this is a simple one here. I just did Cape Town. You guys are at 35 degrees latitude, so that's your maximum sort of annual energy production of latitude tilt pretty much anywhere. I used Swanee City time of use tariff structures, and we get about 2.6 gigawatt hours of PV out of this, electricity out of this thing in a year. This is kind of what a typical load profile looks like in the summertime. You'll be hitting that megawatt kind of base load for a half an hour or an hour during the day. The rest of the time, way under that. And then in the wintertime, looks like there's a little bit more weather, cloudy sky stuff in the wintertime down there as well. So you're not even getting close to that 1 megawatt base load. But you can save, with this system, you could save about 3.3 million rands your first year. Ignore the dollars. One of the things they're very stubborn about over there in NREL is they won't allow you to change the currency.
And
So
can-
everything here is in rands, ignore the dollar sign.
And then PV value, okay.
It's huge, isn't
Over a year,
It's pretty massive, huh?
over 1 year.
Well, so I'm not a financial expert, but that net present value to me is like, is it above zero or not, right? Tells you how good of a investment this thing is, right? So anything positive will give you a return on investment. That kind of a number is huge. It's a little suspect in my mind, but I double checked the rest of the numbers and not too far off the mark. It has a lot to do with, I'm seeing these numbers are getting bigger as our tariffs are increasing.
Thanks, Lawrence. A quick question, maybe a comment. So on the data center that we're constructing in Cape Town, what I'm seeing emerging is a sort of energy center ecosystem approach to it, where there may be multiple sources, energy wheeling on the grid, local generation by diesel, local PV, battery storage. And, I know the DSIR initiated this project to look at green hydrogen, or would be start moving towards green hydrogen. That to me seems very interesting. How does your research extend into the green hydrogen and the storage systems that now need to flatten the curve of the solar?
Yeah, so for the energy, not our team, Manjunath and I don't work directly in those things, but within the Energy Center, there is a team working on batteries. We've had a longstanding team doing some basic research in materials for building batteries. My understanding is that CSIR actually had the earliest sort of working prototype of the lithium-ion batteries, and somehow we sold the patents. I don't know if that's true or not, but so we have Ranesh and his team and Vito in Belgium are teaming up to build a battery test lab here. We want to deploy some large-scale batteries just to kind of do some of the analysis like we're doing here. Does it really work? What are we getting out of this thing? On the green hydrogen side, we've got a colleague, what's his name? Thomas Roos, who's based in Stellenbosch. So certainly love to talk to you about green hydrogen and where that's going.
Is that generating hydrogen from the PV during the day? Yeah.
Yeah, it's basically, I mean, the way I understand it is you get a tank of hydrogen somehow and you hook it up to a fuel cell and you make electricity on site,
Yeah, that's
right?
right.
So the question is, where does that hydrogen come from?
Would I feel happy that in my States Department look after the tank from hydrogen? I wouldn't want to go near that place. Yeah, I mean, nice. Actually, I'm being fair. Actually, be nice about my States Department. They're wonderful people. Nothing will explode. No one will get killed. That's all good.
I mean, it's obviously it's a risk. I think, I'm sure that storage is getting worked out. There's materials that can go into hydrogen tanks. I mean, I saw a regular gas combustion engine 30 years ago that was converted to a hydrogen car. And they were doing the electrolysis. They were doing wind electrolysis, storing hydrogen in the house, filling up their own gas tank with it. This was 30 years ago.
Yeah, I think the efficiency of that's difficult, isn't it? Because that hydrogen doesn't want to come out of water. So I think there are real efficiency issues on how that PV energy, goes split in the water to make that hydrogen. It's not a good enthalpy.
It takes a lot of energy. But where you have excess, renewable resources, and the wind is blowing sometimes, the sun is blowing sometimes, but whenever that's working, it's making hydrogen, which you can deploy anytime. So in principle, it makes a lot of sense. But I just don't know, and I don't know.
So relative efficiency, what's the efficiency of a hydrogen system compared to just batteries?
Yeah.
And the whole economic life cycle cost, and the efficiency of people making those kinds of studies.
Yeah.
Cool.
Good. Yeah.
Yeah, one more piece. So in doing that math, you have to have some. So in doing your math, you need to have some expectation of the life expectancy of the system that you're mathing out. So what is that life expectancy?
Yeah, so from a financial point of view, you have to assign a cost to it, and so we take 15% of the initial CapEx as our replacement cost, and we apply that around year 10. So, but to break that down a little bit, the panels, good panels are gonna last you 25 years, and it's not like they end at 25, they've dropped off to 80% of where they started. They're gonna still go. I mean, when I was working at Sandia, New Mexico, there were some panels that were in the field for 40 and 50 years. Glass was completely shattered, they were a mess, they were still making electricity. So, and then the inverters, those are, at best case, 10-year lifetime, so you're looking at replacing those. If you've got batteries, it's probably, it's a cycle thing, so it depends on how much you're using them, but 7 to 10 years. So you do have to replace components. This racking system is not gonna change much, but we do factor that in. And actually here, where you can see is, for this 1 megawatt system, I assumed about 23 rands per watt, which is actually at the high end. So that's not at all a conservative number for a megawatt scale. It should be under 20 bucks a watt now.
Cool, that's it. Yeah. These slides will be over.
Yes.
Slides will be available.
Yeah, of course, yeah. I'll send, Ricardo has them.
Yeah.
Thank you very much. Just put his in.
Lawrence,
Yeah.
thank you very much. I've got the full token of-
Oh, okay, nice. Nice. So you've got you're working in the UK?
No, just
from the UK.